If you are committed to building healthier, more productive soil without relying on costly fertilizers, subscribe to Husbandry now. Today, we uncover an ancient underground root strategy that can dramatically reduce the need for synthetic inputs while naturally boosting soil fertility. This forgotten technique, used by traditional farmers for centuries, relies on harnessing the power of deep-rooted plants and their interactions with soil microbes to unlock nutrients, restructure soil, and sustain crops season after season. Understanding and applying this method allows modern gardeners and small-scale farmers to replicate time-tested soil health practices that are both sustainable and highly effective. Deep-rooted plants act as natural nutrient miners. Many traditional farmers recognize that certain plants could reach nutrients that shallow-rooted crops could not access. These deep-rooted species, often referred to as dynamic accumulators, draw minerals and trace elements from deep layers of soil and deposit them near the surface as their leaves, stems or roots decompose. By integrating these plants into crop rotations or interplanting them with vegetables, farmers enrich the topsoil naturally. In my own practice, incorporating species such as comfrey, daikon radish, and certain clovers into garden beds transformed nutrient-poor plots into fertile ground, capable of supporting vigorous plant growth without commercial fertilizers. The underground root system improves soil structure. Beyond nutrient accumulation, deep-rooted plants physically enhance soil. Their roots penetrate compacted layers, creating channels that improve aeration and water infiltration. When roots decay, they leave behind organic matter that promotes soil aggregation and encourages microbial diversity. This process, turns dense, lifeless soil into a friable, living medium that's actually capable of sustaining crops, even in challenging conditions. For example, I planted daikon radish along rows with poor drainage. Within a few months, the soil had noticeably loosened, water percolated more evenly, and subsequent plantings thrived without supplemental fertilizer. Applying the technique strategically maximizes its benefits. Timing and placement are critical for success. Deep-rooted plants are often grown in rotation with primary crops or as cover crops during off-seasons. Before planting a main crop, you'll want to allow these plants to grow long enough to develop substantial root systems. Once mature, just chop and incorporate the above-ground biomass into the soil, or, if you prefer, leave it as mulch, allowing decomposition to return nutrients to the soil surface. In areas where mineral deficiencies are, quite severe, repeating this process over multiple seasons gradually restores fertility and reduces dependence on external inputs. The interaction between roots and soil microbes enhances fertility naturally. Root exudates, the sugars, amino acids, and organic acids secreted by growing roots, stimulate microbial communities. Beneficial bacteria and fungi use these compounds as food sources, proliferating and facilitating nutrient cycling. This underground symbiosis releases nitrogen, phosphorus, potassium, and trace elements in forms that plants can readily absorb. By combining deep-rooted plants with organic matter or compost, gardeners can amplify microbial activity, creating a self-sustaining nutrient cycle that supports healthy crops without chemical fertilizers. Practical examples of integrating the underground root secret. For home gardens, plant a combination of dynamic accumulators in border strips, intercropped with vegetables, or as part of a cover crop rotation. Chop and mulch their biomass regularly to return nutrients to the soil. For larger-scale farms, dedicate specific sections to deep-rooted cover crops between main crops to rehabilitate degraded soil. Even in container gardens, incorporating chopped leaves or roots of these species into potting soil enriches the medium and, stimulates microbial activity. Consistent application over time really builds resilience and fertility, reducing the need for purchased fertilizers. Observing results ensures the method's effectiveness. After implementing this approach, just monitor soil color, texture, and plant health. Darker, crumbly soil and vigorous plant growth indicate active microbial communities and nutrient availability. Roots that penetrate deeply and leave channels after decomposition, they signal structural improvement. These indicators allow gardeners to adjust planting densities, species selection, or timing for optimal results. Historical records show that farmers who mastered this technique consistently produced higher yields and maintained soil fertility across decades without relying on synthetic fertilizers. Why this ancient method remains relevant today. Modern agriculture often prioritizes quick nutrient fixes at the expense of long-term soil health. The underground root strategy demonstrates that sustainable productive soil can be achieved through observation, experimentation, and careful use of nature's own nutrient-mining plants. It reduces input costs, strengthens soil structure, and promotes ecological balance, offering a practical path toward regenerative gardening and farming. The broader lesson from centuries of observation. This root-based approach reminds us that soil fertility is not a static property, but a dynamic system maintained by living roots, microbes, and organic matter. By working with these natural processes, we can build soil that supports robust, healthy plants for generations. The knowledge embedded in this technique, honed over centuries, provides modern growers with a blueprint for resilient, productive soil. If this guide inspired you to rethink soil management and explore sustainable fertility strategies, subscribe to Husbandry and share it with fellow gardeners and farmers. The underground root secret shows that by leveraging nature's own systems, you can replace expensive fertilizers, revitalize soil, and cultivate thriving gardens and farms with minimal external inputs.